What's up, everybody? As usual, there's nobody right now, but soon there will be everybody. Okay, we're gonna start in like 5 minutes. If you're watching this not live, I'll put a timer and I'll put a hyperlink in the description. But I also need to continue getting set up. So we'll start here. Let me write down on the board. We'll start at 3:05. We have a viewer, our first viewer. Incredible. Okay, starting at 3:05. I hope everyone's break has been going well. Oh, wow. That's brutal. He left. Just getting organized. Got hella papers. Sad. No one here yet. It's okay. Oh, right. Okay. Still no one here. Too bad none of you get to see my dog. That's your own fault. You should have been here. Okay, so I need to... My setup is like really janky. I need to figure out how to raise this. Oh yeah, and it looks like there's no one here yet, so I'll wait a couple more minutes. Yeah, this is not great. Oh, yeah. There we go. I'm kind of nervous it's going to tip, but it'll be fine. No one wants to run a marathon with me? No one wants to spend their break doing putnam? Oh my god. Hey, we got somebody. Okay. Not just somebody. We got Bella. Thank you for coming. Oh my god. All right. Well, we're not going to start yet, but this is my setup. Okay. Just this massive stack of crap. Okay. Oh, and this one's okay. This is not stable. All my clothes are supporting you right now. I'm sorry. I know. I'm sorry. Wow, this is the least prepared I've been setup wise, because usually I have all my boxes from college that I can stack, but here I'm improvising a lot. So thank you for being patient. So Bella, how's your day? Oh, we have 2. Oh, he's got a flu shot. Okay. Hey, that's not bad. It's better than getting the flu. Okay. I sound like such a dad. We have 3. Oh my god, we got 3 whole people. Oh. Okay, we got 2 now. I should count as a person, right? So we really have 3 total. Kind of weird angle. Okay. I really hope that this doesn't fall. But you guys might get a little surprised. Okay, so just be ready for that. Thank you for being patient, everybody. I didn't think this was going to be so difficult. I'm using all of my clothes to support this. Come on, guys. The Putnam exam is in 1.5 weeks. Where is everybody at? Okay. I know none of you are busy. My dog out. Okay. You know, I'm going to be taking notes. Come on now. Oh my god, this is so like show dog. Oh, she left. I'll show dog if she comes back. See, this is the stack of stuff that is holding you guys up. Okay? The things I do for this channel, sacrifice so much. And what do I get? Get 1 viewer. That's I mean, that's kind of true. All right. Oh, we have 2 people. Let's go. Okay. All right, we're gonna go ahead and start. I know it's past 3:05. Okay, so the main goal for today. Wow, that's rude. The main goal for today is we will be going over 5 Putnam problems. Yes, thank you. We will be going over 5 Putnam problems. Now, this is a lot. This is a lot compared to what I usually do. Usually, I do only 1 problem, and I dig really deeply into it. Okay. Now, usually those streams are like hour and a half, 2 hours. I'm not going to take 10 hours. Okay, I promise. Well, like, I hope. I'm not going to go as in depth, really. Yes, thank you for being here, everybody. I'm not going to go as in depth as I might in one of those streams, but that's just because we're approaching the exam. Okay, really what we want to be focusing on is, yes, 5. Focusing on is like practice, right? And also for people who are kind of new to the exam, this is gonna, I know the last stream I did was only one problem, kind of a light introduction. This is gonna go through a lot of different topics, calculus, linear algebra. It's gonna hit everything. It's gonna be a mathematical, all you can eat buffet, okay? And we're gonna do all of it. Now, the way I have this scheduled is I have 5 problems. I have an A1 and A2, and then we're going to do an A1 and A2, then a B1 and a B2, and then an A3. Okay, so kind of, we got variety of difficulty, and I'm going to go from easiest to hardest. Now, I say easiest to hardest. Obviously, they're all hard. Okay, so if you don't understand the first one, that's supposed to be the easiest, that's fine. You're with most people there. And I mean most in a literal sense, because the median score is usually only, 1 out of 120. Yes, it's going to be very, very delicious. Okay, so without further ado, let's begin this. So the first problem we will be doing, and all the problems are in the description. You can go to Kedlai's archive, and he has everything. So is 2014 A1. Okay, so look that one up. Okay, find it, read it, understand it, unless you're driving. Okay, and that's the first one we'll be doing. So this one is the problem is you want to prove that every non-zero coefficient of the Taylor series of this expression, 1 minus x plus x squared e to the x, you want to prove that every non-zero coefficient is representable, or about x equals 0, is a rational number whose numerator in lowest terms is either 1 or a prime number. Okay, so obviously every rational number in lowest terms, the numerator is going to be some integer, but it's saying here that it's claiming that it's always going to be 1 or a prime number. Okay, and that's what you have to prove. Okay, so how would I approach this problem? Now, also, I'm not going to be the third and final stream I'll do before the actual exam will be much more like abstract, okay, and kind of like higher level. Here, I'm going to focus more on like practicality and just doing the problems. Once we get to that stream, I'll go much more in depth into how I like approach a problem and certain things. But for this one, a good start is always to compute small terms. Okay, so first off, you need to know what the Maclaurin series for e to the x is. Okay, you got to have that on lock. Okay, you got to know that. So e to the x is, of course, everyone knows this. And I'm sorry about the glare, but the sum from k equals 0 to infinity of x to the k over k factorial. Okay, this is something you should certainly know. And so, like I said, a good approach to doing any of these problems is to just compute small terms. For anyone who just joined, we're doing 2014 A1. Actually, I'll just say that in the chat. Also, after each problem, we'll take like a short break because, it's a marathon. Okay. All right, 2014 A1. Now, I'm going to skip this step for the sake of brevity, but really, you should do that. Okay, you should compute small terms. That's something that I'm going to use later down. The only reason I'm skipping that for this problem is because, and again, this is just my own viewpoint. Like I was able to do this without doing that, but in general, that kind of depends on how much experience you have. Anyway, going on a big tangent. The idea is that if we rewrite, so we want to rewrite our expression like this. Okay. And basically, when we expand this out, we don't necessarily know what it's going to look like, but we know it's going to look like it's going to be a power series, right? It's going to be an infinite polynomial. Okay. I guess this is another thing about the Putnam is like you have to get good at looking at something and knowing what it will look like in a conceptual sense. So what we can do is, like, if we think about, so what we basically, if you like, once you expand this out, actually, you know what, I can go ahead and write it. Let me go ahead and write it. So what we end up getting, so the 1 is just going to be the regular sum. Oh my God, we got 5 whole people. Okay. So the regular sum, that's when we multiply it by the 1, right? And again, I'm sorry about the blur. Then minus x times e to the x. And then plus x squared times e to the x. Okay, and you can also write this out, in general, the summation notation isn't like super revealing. Like whenever you think of a sum, you always expand it out in your, or at least I always kind of think about it expanded in my head. But like if we rewrote this, then we'd write, for example, 1 plus x squared over 2 factorial, right? Dot, dot, dot. Minus, now x times this is going to be this. Okay, well, that's redundant. This times x, right? So we write it out. So rewriting this, we get, now I'm going to multiply every term by an x. And in this, we multiply every term by x squared. Now, I hope what I'm doing is not that, there's a lot of terms going on, but really all I'm doing is computing the power series of the expression we were given, which I think, is a very natural thing to do given the question is literally asking about that, right? So I'm just computing it. Now, I need to multiply. So what ends up happening is when you multiply, like when I multiply, the power series by x squared, then the coefficient on the x squared term, for example, is the coefficient on the constant term in the original, right? So like it's like the coefficients are shifted basically by 2. Okay, so like the coefficient on x to the 4th in the original is 1 over 4 factorial, but in this case it's 1 over 2 factorial. It's 2 less factorial, right? That's the concept for like what's going to end up happening once we combine these things. And what we can do is ask, what is the coefficient of the kth term, right? What is the coefficient of the kth term? Now the kth term from the original, okay, so the kth term from, the 1 times e to the x is just 1 over, or the kth coefficient is 1 over k factorial, right? Kth coefficient, 1 over k factorial. Now this is where we have to be really careful. So from the x, when we multiply by x, like if you remember, like and again, like you have a sheet of paper here, you're gonna have everything written down. I have to repeatedly erase it, but like the coefficient of x cubed was 1 over 2 factorial, and the coefficient of x to the 4th was 1 over 3 factorial. So when you multiply by x, the coefficient on the power is going to be 1 less because you multiplied everything by x, so you shifted it all basically to the right. Okay, so what that means is the kth coefficient, the contribution from the second term is actually going to be a minus 1 over k minus 1 factorial. Okay, and again, this is all just pattern recognition from writing things out. Now, once you get, like, I highly recommend writing terms and computing them and such. At least for this problem, I was able to like recognize the pattern without having to do that, but often you really should do that. And in basically every problem I do next, I'm going to do that. Anyway, big tangent. And then the coefficient, or the contribution from the x squared coefficient is going to be k minus 2 factorial. Okay, so, and then it's, minus plus. So this is the coefficient of the kth term. And then, sorry, 1 second. How dare my mother interrupt me during a very important math stream, okay? I'm just kidding. I'll get it later. Okay, so here we want to simplify this fraction, right? Because it's asking about what this fraction looks like in reduced form. Now, this looks daunting, but what you should recognize about factorials, you know, at least if you have experience with factorials, come up all the time in Putnam problems, just in general. Is that if you want to put these under a common denominator, the common denominator is actually just k factorial, because k minus 1 factorial is a factor of k factorial. K factorial equals k times k minus 1 factorial. And, by extension, k minus 2 factorial is a factor of k factorial, because k factorial equals k times k minus 1 times k minus 2 factorial. So that was a lot of words. But basically, when you put these under a common denominator, it's not that disgusting. So here, we pull out a 1 over k factorial. This is 1. This is going to be a k. And this will be a k times k minus 1. Okay. And then simplifying further, 1 minus k plus k squared minus k. And then when I erase this is what I have. I'm just simplifying. I have 2 people. That's kind of unfortunate, but it is what it is. Simplifying further, you get 1 over k factorial times k squared minus 2k plus 1. And when you see that, light bulb should go off in your brain. This is k minus 1 squared. Okay? So our final result for the coefficient is k minus 1 squared over k factorial. Okay. Now, I've also left out important considerations on edge cases. So like, what if k is 0, right? What if k is 1? I know, thank you. Those will be dealt with later, but it's very important that you don't ignore those, because they can kind of, that's the difference between 10 points and 8 points. And like, that is actually a big difference, especially because the cutoffs are usually pretty tight. Like, but anyway, you want to be thorough. Here, I'm being a little loose, but really we have to remember, okay, we have to check the k equal to 0, k equal to 1, maybe the k equal to 2 case. But in general, this is going to be true. So now the question is, why is this always a fraction? Why is the numerator, once I simplify this, always going to be 1 or a prime number? So let's first try to simplify it. So here, we know that there's a factor of k minus 1 in k factorial, so we can take that out. So we can rewrite this as k minus 1 over k times k minus 2 times k minus 3 times 2 times 1, right? So I just took the k minus 1 out of the bottom. And now what you should realize, and again, you should test small cases, right? Plug in values for k, figure out what happens, right? When you plug in values for k, and this will reveal itself. But what ends up happening, what you should realize is that if k minus 1 is a composite number, then, let's say k, let me use an example. Let's say k is 7. Or let's say k is 21. Okay? Then this numerator is 20. This denominator is 21 times 19 times 18 times 17, etc. Okay? If the numerator is 20, that's composite, which means that you can split it into 2 different numbers, which are both less than 20, obviously 4 and 5, for example. And those will be in the denominator, because the denominator includes everything that's less than that. Okay? So again, example k equal to 21, 4 and 5 exist in the denominator. So that means that this will simplify to a fraction which has numerator 1. It'll simplify all the way. And that's what we want. Right? So if k minus 1 is composite, now again, there's a little wrench in this, which I'm going to talk about later. But basically, if k minus 1 is composite, then we can split it into 2 distinct numbers, a and b, which are both, greater than or equal to 2 and less than or equal to k. And a and b will be in this denominator, and we can cancel them out. The only other case is if k minus 1 is prime. If k minus 1 is prime, then this cannot be simplified because if k minus 1 is prime, then none of these numbers are going to have a factor of k minus 1, right? That's okay, Jake. Thank you for coming. None of these numbers in the denominator are going to have a factor of k minus 1 because, let me use an example. Okay, let's say k is 18. Then k minus 1 is 17. So this is 17 divided by 18 times 16 times 15 times 14 all the way down to 1. The denominator is not going to have any factors of 17, and you can show that pretty clearly, okay? Because none of the k minus 2 to 1 will have a factor of 17. And k, if k minus 1 is 17, k can't be a multiple of k minus 1, okay? Again, unless you have an edge case like k equal to 2 or something, but we're going to talk about that later. We're talking about the general case here. So that's the argument. If k minus 1 is composite, then you split it up and you get a numerator of 1. If k minus 1 is prime, then it can't be simplified, but that means the numerator is a prime number, and that's exactly what we want to prove. Now, there's a really subtle thing that I missed when I initially thought of this argument. And this is where, especially with a problem now again, every PUTNAM problem is hard, but if you have, if you feel like you got a solution and you're proud of yourself, oh, I solved this problem and it wasn't even that bad, don't get cocky, because you can often make a really small mistake or miss something on an easy problem. Okay, easy is completely subjective, and that can tank your solution. So here, what we need to think about more is if k minus 1 is composite. So if k minus 1 is composite, then the argument I made was that you could split it into two different numbers, a and b, such that a times b equals k minus 1, and a and b are not 1, right? But if you pick that apart, that's actually not always true, because if k minus 1 was, for example, 9, then you can only split 9 into 3 times 3. And those two numbers aren't different. And there's only one direct factor of 3 in the denominator, right? So the argument actually breaks down. Now, you can easily resolve this, but the point is that I think that it's something that's very missable. And I would guess that a lot of people, when they took this exam, missed it as well. I mean, I was only 12 when it came out, so obviously I didn't do this. But so that's a very important consideration to make. So let's summarize all of that. Now, when you're writing this proof, the first step is this computation. You also have to include, a restriction on k. Say k is greater than or equal to 2 or 1 or whatever you decide. It doesn't really matter, because you can just manually compute those earlier terms with no issue and just check that they satisfy the condition. But this is the argument, which is that, so first off, if k minus 1, now the only case, okay, well, I kind of called that. I was going to tip. One sec. Like I said, my setup is kind of bad. The only case where the composite argument breaks down is if you cannot split k minus 1 into two distinct numbers which multiply to it, right? And the only time that happens is if k minus 1 is the square of a prime. Because if it's, well, first off, it's nice. If it's, not the square of, if, in general, composite numbers, like 20 are going to be 4 times 5. They're not going to be square numbers, right? And those are going to be two distinct things anyway. So you're fine. So you really only have to worry about square numbers. But in particular, if k minus 1 is 64, okay, which is 8 squared, then you can write 64 as 2 times 32, for example. So the only place that you actually have an issue is if k minus 1 is the square of a prime. And if k minus 1 is p squared, okay, then if you look at this expression, k minus 1 over k times k minus 2 times, now, of course, p is going to come up, and then times 2 times 1. Sorry if that's kind of not super readable. So you can cancel. So k minus 1 is p squared. That's the only place that you actually get a wrench in this. Like if it's 9 or 25, for example, then you can cancel one of these powers of p. And then also, I mean, you could, like at this point, you could go one of two routes. So you could, just very easily say like 2p. So you know that, for example, like there has to be another power factor of p in this denominator, because of like if k minus 1 is 25, p is 5. You know that 25 factorial has 5, 10, 15, 20. It has all of these extra factors of 5 that are going to cancel. But I guess the formal argument is that you could say like if k minus 1 is p squared, then you know that k has to be greater than or equal to 2p. Oh, that's really blurred. Something like that. Okay. Or maybe, unless k minus 1 is equal to 4. So you could say like, no, okay. In general, k minus 1 would be larger than 2p. So if in general, p squared is going to be bigger than 2p, right? Unless p is 2. So this is where, so we say k minus 1 is bigger than 2p, because for, p greater than 2. Okay, so basically for any prime greater than 2, any odd prime, this, argument is going to be rock solid. You're going to have another cancellation, and the numerator will be 1. If p equals 2, then that's like a single case. That's k minus 1 equal to 4, k equal to 5. You could just manually do that and just confirm, through computation that you're still fine. Just to do that, if k minus 1 equals 4, then k is 5. So you end up getting, and it's kind of blurred. So you end up getting k equal to 5 gives you, the numerator is going to be 4 squared or 16. The denominator will be 5 factorial or 120. And this simplifies, divide by 8 on the top and bottom, to 2 over 15, which again satisfies the condition because 2 is a prime number. Okay. So we dealt with the k minus 1 equal to p squared case, this edge case, and an edge case of that. Okay. Then you make the standard argument. So you say otherwise, if k minus 1 is composite, okay, so k minus 1 is p squared, we handled that. Then if you say k minus 1 is composite, then k minus 1 equals a times b for distinct a and b. Distinct a and b such that 2 is less than or equal to a and b is less than or equal to n, or something like that, or k. For distinct a and b. So they're going to end up canceling, and then if k minus 1 is prime, you can again make that prime argument. So you can say like, then the numerator is just going to be prime, and you'll be safe. Okay. So that was kind of not as organized as I expected. The big lesson with this problem is that, and this is a big lesson that is going to come up a lot, is that like, there was a good amount of casework here, and there was a good amount of like, kind of, plugging holes, but you need to be okay with that, and you can't do that hastily. Okay. So I say that because I kind of did it kind of hastily because I'm doing the Putnam Marathon. I mean, I did the whole solution in like 34 minutes. In an exam, I have 3 hours, right? But you can't be solving these problems, even if you think that you have the solution, you can't be solving them hastily. Okay. The last problem I'm going to do is going to be a really good example of this. 2015 A3, and I solved it, or at least I got the big breakthrough I needed, and I thought I had the solution, but really it was another like 45 minutes of extra work to really make sure that I had plugged every hole and that I actually was clear in my argument in my head. Because the time between when you get the intuition, when you get an idea, And when you're actually able to formally, rigorously justify that idea, that is a much larger time and space than most people think. So a big mistake that you may make, and I learned this the hard way many times, is that you solve a problem. So you get that big breakthrough and that big idea, and then you kind of rush to get a solution. And then it turns out, oh, your solution was actually wrong, or you ended up spending way longer than you had to. And it's a very frustrating experience because you feel like, oh, you solved this problem, but actually you didn't, right? You need to fully, like, you need to be patient, right? Even once you get excited and you get that big idea. But that was kind of a tangent. So again, big idea with this problem is be careful, be patient. There's a decent amount of casework, some decent amount of exposition here, but again, you have 3 hours, and yeah. Okay, cool. So that was A1. That was supposed to be the easiest one. All right, let's get on. I think that, you know what, I think that the future ones might actually not be as long to explain, but that's a really good Putnam-esque problem. So let's move on to A2. Now, also, I'd recommend, for practice after this, I presented the solutions, sit down and try to write the proofs of all of them. Okay, because everyone knows that there's a big difference between knowing, being able to follow somebody, follow what they did, and actually being able to reproduce that, let alone reproduce a formal rigorous proof with all the details. So make sure you do, I would recommend that afterward. Okay. Let's go to 2014 A2. Now, 2014 A2, let me just explain what this is about. So it tells you A is an n by n matrix whose entry in the ith row in the jth column is 1 over min of I comma j for, all the indices. Compute the determinant of this matrix. So this is again, this is a perfect example of test small cases, right? So what we should do is, what I'm going to do is I'm going to start by looking at different values of n, like n equal to 2, n equal to 3. I'm going to write out these matrices, compute their determinants completely by hand, right? And I'm going to really try to see if I notice any kind of pattern or structure in how I'm doing that, right? So first, let's look at, well, you know what? I suppose we could look at n equal to 1. The really small cases aren't always that revealing, but they can sometimes help with pattern identification. So here, n equal to 1, then you end up getting this matrix, which is literally just this sad little matrix is just a 1, okay? And so the determinant is, of course, just 1. Okay, easy enough. N equal to 2. Now you end up getting, and I'll use the brackets are kind of difficult sometimes. So this is the matrix you end up getting. Okay. If this is just applying the definition. So when I figured, the way that I figured this out was you write each of these as A11, A12, A21, A22. Those are the cells, and then you take the minimum, right, of the row column number, and then 1 over that, and that tells you what the value is. So it ends up looking like that, like 1, 1, 1, a half. Now we're going to compute this determinant. Okay, 2 by 2 determinant, AD minus BC. You end up getting that determinant of A is minus a half. Okay, minus a half. All right. So now let's look at the 3 by 3 case. We still know how to do 3 by 3s by hand. Once we get to 4 by 4s, like, we can do it, but it becomes really a lot of computation, because actually computing determinants, if you're a CS nerd, is an O of n factorial operation. So in general, but it's not always the case. But anyway, let's look at the 3 by 3 case. What I'm doing here is I'm trying to figure out if there's a pattern in these numbers that I can recognize. 1 minus a half. I'm trying to see if, maybe the next number is a third. Then I have this conjecture that the determinants will be 1 over n, and they'll alternate. So there'll be a -1 to the n in that, for example. That's all I'm trying to do with this. And I'm also trying to get concrete examples to understand the structure of this matrix so that I can actually, see what it would look, how it kind of behaves like on the larger scale. All right. So let's look at the n equal to 3 case. Now a equals 1, 1, 1, 1, 1/2, 1/2, 1, 1/2, 1/3. Again, computed it the same way, just list it out, be patient, like that. And then I'll save you the time. But when you compute the determinant using your favorite determinant computing method, either in 3x3 diagonals, I like the diagonals for 3x3, or you do the cofactor expansion, you end up getting a 12th. Okay. So this is actually, interesting. This is actually exactly this is my classwork. This is exactly what I did when I computed this. So I'm kind of just going through my process. Now here, I was kind of, I'm kind of at a crossroads. Okay, so here I'm going to keep this up. So I know that my determinants are 1, -1/2, and a 12th. Okay. Now, with this, I can't really identify a pattern. I don't really know what that pattern would be. So I really have two options. My first option is compute the determinant for the 4x4 case by hand. Now, is that a lot of computation? Yes. But again, you have 3 hours on the exam. It may be worth it to get a 4th term. Maybe if I get a 4th term, I'll be able to actually see that pattern, right? And then have a conjecture about what it should be. Or I could try to tackle the general case. So this is a common sort of crossroads we will meet in a Putnam problem where, at the beginning, you're kind of testing small cases, you're trying to identify a pattern. Then at a certain point, computation becomes very heavy, and you have to decide, do I go to the general case or do I keep on case testing? So here, I was trying to make observations about what was going on. So, let's look at the 4x4 matrix, but let's not compute the determinant. So here, if we look at the 4x4 matrix, 1, 1, 1. And I'm going to present two solutions to this problem, but so here's something I noticed is that this upper left part of the matrix, right, is the 3x3 case, right? That's just the same matrix. And in fact, up in the 3x3 case, 1, 1, 1.5, that's the 2x2 case. So this A is naturally kind of recursive, right? It's a naturally recursive, like sort of the way it's built. So that makes me think, okay, maybe I can use recursion. Maybe I can relate the determinant of A to the determinant of an minus 1. And another big sort of realization I had, I'll explain how I got to this, I think. So if you think about how do you actually compute a determinant in general, you have to use cofactor expansion. But you can't just be doing all this cofactor expansion computation. And when you just try to do it, there's really no pattern that comes out that's really clear. So it just looks like an absolute monstrosity thing to do. And you also, once you reduce it to the n-1 case, then you have to, cofactor expand all those. So I know kind of deep down that to compute this determinant, I need to use cofactor expansion. But I also know that it can't just be the solution isn't just this brute force thing, right? There has to be some way that I can simplify that expansion. And that's when I realized, and again, there are many ways to reach this, that if you've ever done a cofactor expansion and you have, for example, a column or a row where many of the entries are 0, then you want to cofactor expand along that column, because when you do 0 times the determinant of, that term, it's just going to be 0. So like if you have a lot of zeros on a row or column, cofactor expansion is going to simplify a lot. So I'm thinking like, okay, how can I make that happen? And then I realized that when you from linear algebra, you should know this, when you subtract or add rows and columns, you don't change the determinant. So if you replace a row with a linear combination of the other rows, or the row, then it's not going to change the total determinant. And that's when I realized, okay, if I subtract this row, or if I guess what I did was, if I subtract this row, wait, let me look at this. If I do like this minus this one or something, then I can get a 0 here. So here, let me make sure I know exactly what I'm saying. So let's redraw this. So here what I'm gonna do is I'm gonna do shoot, I'm trying to remember. I think here, sorry, let me quickly. Oh, I think I have it here. Okay, so okay, yeah, okay. So what I can do now, and so another thing that's making me think about this is the fact that I already, like I said before, A is this naturally recursive structure. So like if I do a general cofactor expansion, then I can have like one of the terms will be the determinant of this matrix, right? And I already presumably know how to compute that. If I have, that's like kind of the concept behind recursion, right? Is that you assume that you know how to compute the thing before. So that's another thing that made me think to use cofactor expansion. Here, if I replace this row with this row minus this row, then all of these terms cancel and I get a row that's almost all zeros. And I also preserve this upper matrix here because I don't want to mess with this because this is what's going to let me do the recursion. So here, I'm subtracting the bottom row. So R4 replaced with R4 minus R3. So first 3 rows, nothing happens. But the fourth row, R4 minus R3, that's going to be 0, 0, 0, and then a fourth minus a third, which is minus a 12th. And here is where the magic is going to happen, okay? Because what I'm going to do is compute this determinant using cofactor expansion, but I'm going to expand along this bottom row. The only term that's non-zero is the one associated with this term, this cell, and that's going to be times the determinant of this upper left matrix, which I have, which means I can generate a recursive formula for this. So what I can say is that also, in general, right, 12, what does 12 have to do with 4? Well, okay, actually, wait, I'll explain this later. 12 is 4 times 3. That's going to come up later. So what I have is that the determinant, so d sub 4 equals minus a 12th times d3, right? And d3 is just a 12th, so this is going to be minus 144. Okay, and I have a general way to do this. So when I think about the general case, the process that we did, we took the last row, we replaced it with, so we took r sub n, we replaced it with r sub n minus 1. And all the terms are going to cancel to 0, except the last cell. The last cell is going to be 1 over n minus 1 over n minus 1. Okay, which simplifies to minus 1 over n times n minus 1, if you put it under a common fraction. And this is like, you should like, in my opinion, this is something you should like know, like you should just have down. Like if you do 1 over 4 minus 1 over 5 is 1 over 20. So 1 over 4 minus 1 over 5 is 1 over 4 times 5. 1 over 6 minus 1 over 7, 1 over 42. So like this is a simplification that you should know, and that it comes up a lot. But that's what this is going to be. So in general, we have d sub n equals minus 1 over n times n minus 1, d sub n minus 1. And then the base case, d sub 1 is just 1. Okay, because like the 1 by 1 matrix determinant is 1. So now we have a recursive formula for computing this determinant. Okay, and now what's left to do is get the explicit formula. A couple ways you could do this. As always, plugging in values of n and just computing it, okay, to see a pattern, always a good move. Okay, here I'm gonna kind of skip some of that just to get to the general formula. So what I'm going to do is say, I know that dn, actually, you know what? No, I'll use an example. d7 equals, okay, so now we got all these minus signs going on, right? So that's going to culminate in a factor of, so like we have all these minus signs, and d1 is positive 1. So all of the even determinants will be negative, all of the odd determinants will be positive. Because you just get a factor of minus 1 to the n minus 1. Okay, so this is going to be minus 1 to the 7. Now I can focus on the 1 over n times n minus 1 part. Actually, wait, so minus 1 over 7 times 6 times d6. And d6 is minus 1 over 7 times 6 times minus 1 over 6 times 5 d5. Right? And then if I just, apply the recursive definition all the way down, then what we get at the top is we end up getting 6 negative signs. Okay? So we end up getting minus 1 to the 6, which is positive, times the denominators are going to look like, it's going to be like this. So 1 over 7 times 6 times 6 times 5 times 5 times 4 times 4 times 3. And then there's only like a couple more terms, but times 3 times 2 times 2 times 1. Okay. I'm just expanding it out. And this here, it looks like 7 factorial, but we actually have copies, right? So we actually have two copies of that. So one way there's many ways you could write this. You could write it as 6 factorial squared times 7. You could write it as 7 factorial times 6 factorial. I mean, it doesn't really matter. They're all equivalent. The way that I chose to write it is that this is 1 over 7 factorial times 6 factorial. Okay, that's what it simplifies to. And so from this, we can get a really nice conjecture for what we think the formula is going to be. Okay, because the 6 is 7 minus 1. Then this is just the 7, and this is n minus 1. So I'm going to conjecture that dn is equal to minus 1 to the n minus 1 over n factorial times n minus 1 factorial. All of this is extrapolating the pattern that I saw from the test case, right? And then, of course, to prove something like this is easier than to figure it out. All I need to do is show that this satisfies the base case and that it satisfies the recursive definition, right? So d1, and you just do that by induction. So I think I might skip that, but basically d1 is minus 1 to the 0 over 1 factorial, 0 factorial. So this is just 1. Check. Okay, base case works. Then we had that recursive definition, and you can show using induction that this satisfies the recursive definition. And so this is our answer. Okay, this is how we compute the determinant. All right, so that's the way that I did it, right? I'll show another solution. That won't take too long, I think. So again, for practice, I would recommend actually doing this using going through the induction and proving this. But that is, the formula. And also you can check that this works. So a good thing you should do at the end of, when you get a formula like this, you should check that it actually works with the test cases that you did manually. So if we plug in n equal to 1, n equal to 2, and 3, this is going to satisfy that. So we can be kind of confident that it's correct. All right, so let me show the second solution. Kind of relies on the same idea. So here, if we look back to this matrix, let's look at A4. So another thing you can realize is that computing a determinant of a matrix is very difficult, using cofactor expansion, very computationally difficult. But unless the matrix is upper triangular, okay? Upper triangular means it has entries on the diagonal. In the upper right corner, you can have whatever you want, and in the lower left corner, it's all zeros. And the determinant of an upper triangular matrix is the product of the entries on its diagonal. Okay, and you can prove this through cofactor expansion, I think. Another exercise left to the reader. Okay, prove that. But I think it's well known enough that you can cite it. So if we look at that, another person could look at the situation and think, how do I make this upper triangular, right? So here's the matrix A4. Now I kind of jumped the gun a little bit because I saw an opening. Okay, and I went for it. I think that's, I think my solution is, obviously I'm biased, I think my solution's fine. But this one, you may fancy a bit more, okay? So what I did was I subtracted, I replaced R4 with R4 minus R3. Doesn't change the determinant. Is that even readable? Like, I think it's okay. Like, so this becomes all zeros and minus 1/12. But what if we did the same? What if we replaced R3 with R2 minus R3 with R3 minus R2? And again, the reasoning behind this is that you're thinking, if I make this matrix upper triangular, I can get the determinant, right? So here, if I do that replacement, then these terms will cancel, right? These front terms will cancel to 0. And we end up getting minus 1/6. And this is minus 1/6 as well. Okay? Then we do the same. This becomes minus 1/2. These all become minus 1/2. And then the top row, we do nothing. And this is an upper triangular matrix. Okay? Because, boom, there's your triangle. Okay? There's your triangle. It's kind of really badly drawn, but these are all zeros, right? And so what that means is that the determinant of A4 is product of the entries on the diagonal, 1 times minus 1/2 times minus 1/6 times minus 12. Okay? And so, you can multiply that, you end up getting it's 1/144. Now, in general, as I discussed earlier, these, like each term, this is 1/2 times 1, 1/3 times 2, 1/4 times 3. So 1/k minus 1/k minus 1 is 1 minus 1/k times k minus 1. Okay, so here you can sort of like rewrite it in that way. So you can rewrite this as, now you get 3 minus signs, and it's A4. So if n is even, you end up getting an odd number of minus signs, right? It's like the minus 1 to the n minus 1, right? So you end up getting a minus 1 to the n minus 1 out front. And then the fractions, I guess I'll just put it all in the denominator. So you end up getting minus 1 cubed over, this is going to be 4 times 3, 3 times 2, 2 times 1. And this, like I said, you can write it in many different ways. You can write it as 3 factorial squared times 4, whatever. I'm going to write it as 4 factorial times 3 factorial. And here we can conjecture what the final answer will be. So we conjecture looking at, I just erased it, but that was 4, this is 3, this is 3, this is 4. So we conjecture that all the 3s are n minus 1s and all the 4s are n's. We conjecture that we have dn equals minus 1 to the n minus 1 over n factorial times n minus 1 factorial. And that's the same formula we got before. And in fact, actually, this is not a conjecture. You could just compute this explicitly. So what you say is the argument that you make is that you say, okay, replace row n with row n minus 1, and then we want to replace row n minus 1 with we want to replace row n with Rn minus 1. Then we want to replace Rn minus 1 with Rn minus 1 minus Rn minus 2. Then we do these replacements, and you would say, do this for all, I don't know, it's like a loop, right? So you can just say like, make J, I guess you would say, it's probably enough to just say repeat this process if you don't want to be too rigorous. And then you basically say, when you put RK minus 1, this is the important thing, the first K entries will be 0. Is it the first K? The first K minus 1 entries will be 0. And that is what produces the upward triangular shape. The fact that, that here the first is 0, first and second are 0, the first, second, and the third are 0. And then you say, okay, well, then it has to be upward triangular. So the determinant is the product of everything down the diagonal. And then you compute that. So you express that product, and then you compute it, right? Okay, so two different solutions, same answer, obviously. Two different, little different styles, okay? The second one is more like, maybe like more elegant or whatever, right? Because you're not relying on like recursion and deduction. But in my opinion, like recursion is so powerful in a lot of cases that if I see an opening and I see like, okay, I can do this, then I'll usually just kind of go for it. All right. So that was 2014 A1 and A2. Okay, so I'll take a quick break, couple minutes. Because this is a marathon. Okay, water break, right? Gotta hydrate. And yeah, and if you want to like blow up the chat or you have any questions, I don't know if I've ever gotten a question in the chat. So, whoever wants to be the first person to ask a question, you can ask a question in the chat. Oh wait, actually, Ryan said 5. Okay, so let's. I'll be back. Well, I'm gonna be here, but we'll restart again at 4:05. It's not much of a break, I know, but that's what we'll do. So yeah, I know I'm probably going kind of fast. Like I said, this is like I'm presenting, I don't know how to say this. Like you have 3 hours on the exam. You have 3 hours. So, I just did both of those in 1 hour. Most people won't get one problem. So like, you shouldn't expect yourself to like get a solution this quickly. I didn't, because I had to solve it myself. I'm just kind of presenting the solution. But yeah, like I said, for practice, you should, I think, oh, how was your day? Thank you. My day's been okay. I was kind of tired when I woke up and I didn't take a nap. So it's kind of tragic, but I think I'm doing fine. Well, I don't know. I hope I'm doing fine. I'm probably going kind of fast, but I've realized that I don't really get to the point like sometimes. So I'm trying to do that. So yeah, so I woke up, then, morning routine. Okay. Ate breakfast, showered, all that. Then I did some Putnam problems. Obviously, come on now. That's how you have to start your day every day. I prepared for this a little bit, and then I did 2014 A3. I did not complete it, but I only gave myself like 45 minutes to work on it. Then I played with my dog. I'm not oh my God. You asked, okay? Yeah, that's what? No, I mean, I hope I won't be cranky. Yeah, like so the Putnam exam, if you're planning on taking the exam, it's in 1.5 weeks. So, just make sure that you're kind of mentally, getting ready for that. You shouldn't necessarily be like you don't want to be nervous, but it is, you want to make sure that like it's not a surprise. Like, oh shoot, you don't want to go out partying with your friends Friday night, don't get back till 4 a.m. and be like, oh shoot, I have the Putnam tomorrow. Like that's one thing you want to make sure you get sleep for and you're mentally ready for. But I am very happy that there's so many people taking it. At least I think. I actually don't know what the signups are like, but that's really great. And we could actually do well. Like I know that in 2015, Pitt got like 42nd. Just like it's not MIT. 40, get hyped, exactly. I saw this video on YouTube of this college that literally had a pep rally for their Putnam. Like the math club had like an actual pep rally, and it was super goofy, but like it was great. You should definitely look that up. And it was like some small college too. It wasn't like MIT or anything. Yeah, at MIT there's like 130 people that take it, and that's just like this is insane. There's this picture of all these people taking the Putnam like in this massive gym. I mean 130 is not like 130 is a good amount of people. And they basically all get in the top 500, which is the sad part. But anyway, going on a tangent. I think that we should get going on 2009 B1. Pick a never. I mean, no college, even Harvard. Even Harvard only has maybe a couple dozen people in the top 500. Like MIT is just so good somehow. Okay. So now let's look at 2009 B1. So now we're going to the B section. Then when we finish, we'll go back to the A section for 2015 A3. Now that's going to be a toughie. Okay. 2015 exam is already really hard. But that's also for me to, that's also for my own review as well. All right. So B1, 2009. What's going down with this one? Okay. So this problem, 2009 B1. I meant about that pep rally. Oh, I mean, I don't know. That's like I'm hyped for the Putnam, but like I don't know. It's kind of pep rally seems a little too corny. Even for me. So B1 is show that every positive rational number. Oh, I'm supposed to type these things in the chat. We just did 2014 A2. Show that every positive rational number can be written as a quotient of products of factorials of not necessarily distinct primes. Great. Okay. Now, it's fine if you didn't get that. They give an example, and I think it explains what's going on. So they give the example, 10/9 equals 2 factorial times 5 factorial over 3 factorial times 3 factorial times 3 factorial. So basically, this is like a number theory problem. What we want to show is that any rational number you give me, I can write it as another fraction where it's a product of factorials of primes. So product of factorials in the numerator and denominator, but these numbers all have to be primes. So 2, 3, and 5, they're prime numbers. Okay. So this is initially kind of daunting, right? So, but a strategy which I'm really emphasizing a lot more this go around is testing cases, testing basic cases. Okay. So here it's asking for us to prove something for every rational number, positive rational number. Why don't we start with the integers, the positive integers, and why don't we just start trying to generate these representations? Okay, because maybe, now again, the whole point of doing this is we're generating these representations. We're trying to see if we can see a pattern, or, we're trying to make observations about what's going on. It's not just like this mindless listing process. You're really trying to be on the lookout for a pattern or some piece of logic that you can use in the general proof. So let's start with 1. How can we write 1 in this way? Well, why don't we do 2 factorial divided by 2 factorial? Okay, easy enough. Right away, you could also do 3 factorial or 5 factorial, whatever. Not super revealing, but you got to start somewhere. Okay. 2. Now this one, surprisingly hard if you don't think about it. And this one, you actually are going to write in this way. Now this is after you've played with it a little bit. Okay. So this is after you've done the problem. 2 factorial times 2 factorial divided by 2 factorial. So that's a little tricky to think about because, like, you usually don't write fractions in that way. Like, you usually don't just have this thing that you can cancel, but that's how you write 2. Let me look at my work. I did this today. So 3 we can write as 3 factorial divided by 2 factorial. Okay. Then 4. Okay, so this is what we have for 1, 2, and 3. Then 4 we can write. 4 we can write as 2 factorial, 2 factorial, 2 factorial over 2 factorial. Okay, and then we could write 5. Now, okay, the way I'm explaining this, I'm like, well, we're writing 1, then 2, then 3, then blah blah blah. I'm actually, like, when I'm actually doing this problem, I'm thinking about how I can generalize this to rational numbers, right? And how I can actually, what is my thought process for generating these things? Okay. So here we could write it like 5 factorial over 2 factorial, 2 factorial, 3 factorial. Now, once you're doing this process, again, in the back of your mind, you want to be thinking about, how do I actually solve the original problem? How do I get all rational numbers? And what you should realize is that, let's say I have some rational number, 5/4, that I want to get a representation for. Then I can actually just use 5's representation I can put in the numerator, and I can divide by 4's representation. And you get a compound fraction. But once you simplify that compound fraction, it satisfies the conditions of the problem, right? So here, right, what I've kind of realized, what I realized was, if I can show that I can represent every positive integer, I can, by extension, show that I can represent every irrational number. So I've reduced my problem to just the integers. So again, so here, like, let's say 5 is a over b and 4 is c over d. Okay, and this is, in this case, it's these representations I've written. Then I can write this as ad over bc. So I can multiply the compound fraction. Okay, you can simplify it and you get a representation for 5/4. It's very unwieldy, but it still works, right? All right, so here what I've done is a big simplification. I've shown that I only need to find the integers, and then I can combine representations to generate new ones. So now I'm thinking, can I do this again? Can I do this further, right? How can I combine representations to generate new ones? Why don't we look at 6, how we represent 6? Well, the principle I just used was that to do 5/4, I can use 5 and you can use 4, I can combine them, I can divide them. What if for 6, I already know what 2's representation and 3's is, so what if I just multiply them? 6 is 2 times 3. What if 2 is represented in this way, A over B, and 3 is represented in C over D? And then I can write 6 as a representation as AC over BD, right, in the same manner. So that's also a big deal. What that means is any composite number we can split into 2 divisors, right? And we can write that as so any composite number we can write as a product of 2 of its divisors, which are, both not 1, both not the number. And then we, for example, here I'm thinking, okay, induction, right? Because here I'm thinking, how can I apply induction? Because, I'm kind of working under the assumption, like, if I'm trying to figure out what 6's is, then I already know what 2's and 3's are. Okay. Then if we know these, then we can get 6. Okay. So now all I have to do is figure out the representations for all the prime numbers. Because once I do that, I can write every number in, for example, its prime factorization. And then each of those prime components, I have the representation. Then I exponentiate them and multiply them and everything. And I get one big representation for that number. So now all I need to do is figure out, how do I represent every prime number? Okay. How do I represent every prime number? So let's look at 11. How do I represent 11? One thing you know for sure is that you know the numerator. Well, okay, so the thing with factorials, there's a lot of things with factorials, okay? One thing with factorials is that like 11 factorial is the first factorial that has a multiple of 11. Okay, and that sounds obvious, but 10 factorial is not the first factorial that has a multiple of 10. The first one is 5 factorial, because 5 factorial is 120. So like whenever you get whenever you have a prime factorial, then that's the first time you get that new prime. All right, it's the first time you get the new prime. So I know that 11's representation has to have an 11 factorial in it. It also can't have like a 17 factorial, because now I've created a 17. And the only way I can get rid of I can't get rid of a 17, because that's also another new prime. Unless I have unless I have like a 19 or something. 19 factorial, which cancels 17. So I'm kind of going on a tangent here, but I think, you kind of get the idea. Like, now you don't actually need to prove that this needs to be the case, but this is my thought process for generating this representation. All I need to do is show that I can actually find a representation. I don't need to show that it's the only one. So here, 11 factorial in the numerator. In the denominator, I need 10 factorial. Now, how do we represent 10 factorial, right? Under our induction, this doesn't really work. Okay. Well, what I can do is write 10 factorial, because 10 factorial is way bigger than 11, as 10 times 9 times 8 times 7 times 2 times 1. And presumably, right, under the inductive hypothesis, I know how to represent all of these numbers, 10, 9, 8, 7. I know how to represent all of them. So I can multiply all of their representations, combine them together, get a big compound fraction, rearrange it, and I have a representation for 11. Okay? So that's the logic. Okay? The whole principle of this is once you have, how can you basically reduce the problem size, right? Reducing the problem size is a big principle. And also how you can, this is a form of induction. You need to have really good intuition for induction and when you can apply it and stuff, especially for PUTNAM problems. So if you've learned induction, which if you don't know it, you should definitely learn it. You kind of learn it as dominoes or something, right? P of 0 is true and P of k implies P of k plus 1. So then, P of n is true for all n in n. That's the way you learn it. And you kind of learn it as this very linear thing. But in reality, induction, you can, inductive thinking, and not inductive thinking in the sense I kind of learned that in the scientific sense, but inductive thinking in a mathematical sense can be very nonlinear. And you can kind of just, you want to have an intuition for what you can just assume. I'm just assuming, okay, I know 10 and everything down, right? Because I'm using this inductive thinking. Okay, so that's the argument, kind of. Now we need to look at how we actually prove it. So the way that I would prove this is, so we need to show that it's true for all integers. We know how to, we say, okay, if we know for all integers, we can get the representation for all the rationals. So here I might actually just want to use just induction, like actual linear induction. So what I can say is, I can define P of K. So, okay, there's a couple things you could do. You could either, you could show that you can represent every prime number, and then say every other number you can write in its prime factorization, as a product of lower primes. Then you get their reps. So then you get all the integers, and then all the positive integers, and then you get all the rationals. That's one. So you can induct on the primes. You can also just induct on every integer. And once you get, your inductive step, once you look at k plus 1, you can say if k plus 1 is composite, then I can represent it because I can split it in two, right? I can split it into two factors. If k plus 1 is prime, then I make the argument I just made. So then you can use linear induction. So you can, actually it needs to be strong induction. So here, define P of K as the statement that J is representable for all 1 less than or equal to J less than or equal to K. That's the statement, okay? Then you say, okay, P of 1 is true because 1 equals 2 factorial over 2 factorial. Base case. Essential. Usually not too bad. Then you assume P of K, or some other variable. Doesn't matter. Or I guess I should use n here. It's kind of standard. Okay. So then you assume P of K, and then you say, okay, if k plus 1 is composite, I split it into two numbers which are lower, and then I get their representations, multiply them. If k plus 1 is prime, then I write it as k plus 1 factorial divided by k times k minus 1 times k minus 2, etc. Each of those numbers are representable by the inductive hypothesis. So then I can multiply them to get a big compound fraction, simplify it, and get a representation for k plus 1. And so then you end up with a very basic inductive proof. P of 1 is true. P of k implies P of k plus 1. Therefore, P of n is true for all n in n. Okay. So yeah. So I guess another sort of lesson here, and this is a marathon, right? So I'm not really digging super deep into a lot of big ideas here. But I guess one takeaway that you should recognize is that, we sort of solve, a lot of times you'll solve the logic for a problem. And then when you're thinking about how to write the proof, that's a completely different mode of thinking. Like when you're writing the proof, when you're thinking about how to write a proof, a lot of times also you're thinking about, okay, how clean is this going to be? Cleanliness and efficiency in your proof are important for two reasons. One is time. 3 hours is a lot of time, but it's actually not. Okay, because these are detailed problems, right? And when you're writing a proof of a detailed problem, it can take you 30, 45 minutes, for example. So one is time. Two is the more efficient or clean a solution is, the less likely you are to make a mistake in proving it. Okay. Also the more clever your solution is, the shorter it is, more likely it is that you're going to get the full 10 points. Now, I say that with a massive asterisk because you could miss, if you miss edge cases or you totally oversimplify the problem, then no, you're not going to get your 10 points. But I think you understand kind of what I'm getting at. Some Putnam problems I've done for practice, some of them I've written, 5-page proofs, for example. And now on the other hand, right, having a really long proof isn't always bad because if you can solve the problem and you can write a proof, even if it takes you 5 pages and you can get your 10 points, then that's 10 points on an exam where most people only get 1. So you have to kind of balance those two kind of ideas. Basically, once you feel like you solved the problem, you need to really slow down and you need to keep going with the problem. You need to think, okay, can I simplify this even further, right? Can I simplify my logic even further so that when I write the proof, it's as clean as possible, right? That's something I'm going to talk about like in the last session I do. All right, so let's enough of that problem. Let's move on to B2. I might take a really short break. I don't know how many. There's 3 people here. Okay, people are really coming in and out, which is okay. But so next we'll do 2009 B2. But for now, we'll take a really just a quick break. Okay. Another thing about, and again, I'm going to talk about all these things in a structured manner later, but another thing about case testing is that a lot of people, when they take, like let's think about here. Let's think about the last problem we just did. So a lot of people will want to dive into the general problem. They're gonna look at, okay, let's say I have a rational number R. I write it as P over Q, and then they try to they try to construct the products from these variables P and Q. So a lot of people will just dive in and try to tackle the general problem right away. They won't start with, okay, why don't we just write 1's representation, write 2's, write 3's. They won't start with this case testing. And this is something that I did before a lot too. And it's sort of kind of like it's like rooted in a bit of cockiness, like, oh, I'm too smart to like just generate these cases. Like I don't need to deal with that. I can just work on the general solution. And really you can't get into that mindset. Like writing examples and actually getting concrete numbers in your face, patterns are going to show themselves to you way more quickly and in a much clearer manner. And really that's the smart thing to do, is to not just dive in with the general problem. So that's another thing about case testing. You have to humble yourself a little bit. A lot of people think that they're too good for it, but it's really the good thing that you should do. The reason I'm emphasizing it so much is because that's something I didn't really think about, like when I first started studying for the Putnam, and also like only up until like recently, I always kind of thought very abstractly about the problems, and I never really focused on the practicality aspect. But really, solving a problem like this, you have to have the right balance of abstract, high-level thinking, conceptually what's happening, right? But also like practicality, like what do I think is going to work, right? And what's actually, like getting numbers in my face. That's a very like engineer way of thinking, and not like like a mathematician way of thinking. In fact, actually, like this is kind of funny, but like the formal term for like for computing small cases to identify a pattern and then getting a general formula is called like engineer's induction or something. Because like you're technically not proving induction rigorously. Obviously you write the proof afterward, but like let's say I had like, okay, here's my pattern, 1, 1/2, 1/3, 1/4. And then I say, okay, general formula is 1 over n. If you stopped there, that would be like engineer's induction. Okay. And some people make fun of it, but it's actually like a really good strategy. Of course, then actually you have to prove the formal induction. All right. We're going to break for 2 more minutes, and I'll actually be quiet this time. And I was just talking for most of that. Okay. I'm going to talk again. I expect that we'll be done by maybe 5:30 or 5:40. We're going at about 30 minutes per problem. The last one is a little longer though, so it's harder. So that's actually what I was aiming for, which is good. We have a guest. My dog has joined. I know someone asked. Oh, yes. Bella asked about the dog. So showing the dog. All right. Let's go ahead and let's get back into it. Okay, good. We got it. The comment about the dog. All right. Okay, so now we're trekking into more difficult territory for sure. B2 and A3. Now, like I said, all the problems are hard. Don't get discouraged. Okay. Me saying that it's more difficult territory is completely subjective to my own ability level. But let's take a look at B2 of 2009. So this is I really like this problem. I won't lie. There are so many problems that I like. You know, wish I had the time to talk about all of them. So let me type that in the chat. All right, so let's look at this problem. Let's look at this problem. It's defined as a game. Now the game is that there's only one viewer. It's okay. The game is that it involves jumping to the right on the real number line. If A and B are real numbers and B is greater than A, then the cost of jumping from A to B is B cubed minus AB cubed. Okay, so the game is, you're jumping to the, you're jumping from point A to point B, and the cost of that jump is B cubed minus AB cubed. It's just some quantity. The question is, for what real numbers C can one travel from 0 to 1 in a finite number of jumps with total cost exactly C? So what we're doing is we're starting at 0. We're going to jump to 1. We can do whatever we want in between. And the question is, what are all the values of C that are attainable, the total cost? Okay. As always, let's just think about generating some cases. So simplest thing we could do is just jump from 0 to 1. The cost is going to be B cubed minus AB cubed, right? So 1 cubed minus 0 times 1 cubed. So the cost is 1. Okay. So one jump, the cost is 1, right? Now, if we use 2 jumps, and let's use 2 jumps and make them completely evenly spaced. So this is to 1/2. 2 even jumps. Now I'm just going to write 2 jumps. The cost would be, let's compute it. This is going to be 1/8 plus 1 cubed minus, so 1 minus 1/4, 3/4. The cost is 7/8, I think. Does that seem right? Yeah, I think that's right. Yeah. Wait. No. This is so 1 cubed minus 1/2 times 1 cubed. So that's just a half. So this is going to be 5/8. Okay. We could also, so I'm just computing. Okay. we could also, for this two variable case, we could say, okay, what if we had two jumps and we actually didn't make them evenly spaced? And this is a good question to ask because this is actually going to give us a continuous range of values. So we were only generating single values here. We need to get a continuous range. So let's say that we jump to point X. So we go from 0 to 1, or to X to 1. Okay. Then the total cost, C, is X cubed plus 1 minus X squared. X cubed minus X squared plus 1. And X can range from 0 to 1. And then the question is, okay, what does this graph look like? And basically for this, so one question we can ask is like, I guess, no, okay, wait, we know how to graph this kind of. Okay, so what we could say is, here's 0 and here's 1. We know the cost when C equals 0 is 1, and when C is 1, it's also 1. So our graph has these 2 points, and then we can ask, okay, what does it look like in between? So why don't we try to find the critical points? Why are we trying to find the minimum of this? Okay, to find the critical points, set the derivative equal to 0, solve the quadratic. You end up getting something kind of weird, like, so you end up getting, this is your function. Okay, you only get one critical point, and it's like, I forget what it is, like 2 over 3 square root of 3 or something when X equals this. And then you essentially get a minimum value, okay, for that. So this method, this is nice, okay, because what we've done is we've actually produced a continuous range of values. We've shown that everything from the minimum of this graph to 1 is attainable. But the question still remains, can we go any lower? And this is where this process starts to get complicated, because if we try to add a second arbitrary point in this jump process, say y, okay, then you end up getting a function of 2 variables. And to find the critical points of that, that's kind of gross, okay? And of course, in general, there's no long-term strategy here, because if you have n variables in general, then you're going to get a really, an n variable function finding the minimum, and it's going to be kind of terrible. So we want to think of another approach to this problem. So let's say that, let's take a look at this thing, b cubed minus ab squared, this cost value. So looking at this, right, we can, natural thing to do is to factor this to b squared times b minus a. Okay, so let's say that we have, and again, the blur is really bad. So our cost from jumping from b to a is b squared times b minus a. Now let's say that we have a sequence of jumps, okay? 0, here's 1, and then we go to x1, x2, x3, and then xn to 1. Or let's say, so x0 is equal to 0, xn is equal to 1. And then this is xn minus 1. Okay, so that's probably not visible, like, at all. Shoot. Well, anyway, you get the idea, okay? Sequence of jumps from x0 to x0, 0, xn is 1, sequence of jumps in between. So here, we can write total cost as the sum of, from I equal to 0 to n, of xi squared times xi minus xi minus 1. Okay, from the factorization. And really, the key insight here is to think about, okay, you also, subconsciously, you're also thinking, okay, what happens as n goes to infinity? Like what does the cost equal when n goes to infinity? And like if you look at this, right, this sum here, and you look at it long enough and you think about, where have I seen this before? You eventually, hopefully, realize that it is a Riemann sum. Okay? This is actually a Riemann sum. And in fact, a Riemann sum of y equal to x squared. And we don't actually need to push n to infinity to recognize this as a Riemann sum. Right? So if we just look at this here, given 0x1 up to xn, that's actually going to define a Riemann sum of y equal to x squared on the interval 0 to 1. So what we've done is we've actually reposed the question in a way which is more sort of, we have more experience with. It doesn't seem so arbitrary, which is that the question becomes, what are the possible values of all of the Riemann sums of y equal to x squared on the interval 0 to 1? So here, and I guess I should have kind of said this. So this here is your delta x for the Riemann sum, right? This is your width of the rectangle. Your height of the rectangle is xi squared, right? Because you're looking at the function y equal to x squared. So looking at this, right? So, and I'll draw the picture too to just make it more clear. So here's 0, here's 1, here's 1. Y equal to x squared. Okay. And let's say, we have, here's x1, here's x2, here's x3, and 1 is x4. Then if you look at, now it's a right-hand Riemann sum. So if you look at this point here, this has function value x1 squared, and the width is xi minus 0, right, is b minus a. And then we do the same for this. So here, area of this rectangle is b minus a times b squared, right? And then we end up getting this final one. Okay. So now we posed a much more interesting question. Well, I mean, I think it's a more interesting question, which is, what are all possible values of this Riemann sum? So first off, I think the first thing you might want to compute is, what is the value as n goes to infinity, right? That's just the integral from 0 to 1 of y equal to x squared, which ends up being a third. Okay, so you should be able to do that integral. That ends up being a third. So a third is the minimum, and a third is not actually attainable, right? Because we need to use a finite number of these rectangles. So, and we also know kind of that, like, we have an intuition that the max, like the worst Riemann sum you could possibly do for this, the biggest overestimate, is if you just had one massive rectangle, right? You only use one jump. So the max is 1. So we conjecture, so we say, okay, the min Riemann sum, or I could say infimum, but you might not know what that is. The min is a third, the max is 1, and a third is not attainable, and a 1 is attainable. And intuitively, we can get everything in between, right? So intuitively, we think, okay, we should be able to get every real number in between 1 and a third. So this is our conjecture for the answer. And it proves to be a much more difficult problem than maybe it looks. So we know we can get very close to a third, and we know we can get 1, but how do we actually prove that we can get everything in between? How do we actually show that if you told me 0.78932, that I could construct a Riemann sum that has that exact value? Here, let me get another marker. And so this is the big question that we're going to be trying to answer. Okay. Oh, I know where my markers are. So I'm also going to discuss a second common approach to this problem, which you can prove is not going to work. Okay, so let me explain what I mean. So one approach that I thought of was like, what if we just made these always evenly spaced? So we basically said, like, okay, so we could have 2 evenly spaced jumps, 3, 4, 5, 6. We could have, has however many evenly spaced jumps we want. That's going to give us an infinite number of total costs, and that's also computable. So if you compute it, you can use you can use the formula for like 1 squared plus 2. So you should know this. 1 squared plus 2 squared plus up to n squared is n times n plus 1 times 2n plus 1 over 6. Okay, so you got that formula, so you can compute this. So this was something I thought about, like, why don't I just try pursuing this? And I have no doubt that at least a few people on the exam, when they took it, tried pursuing this approach, tried to generate every number. So it said, okay, because they may have also identified the Riemann sum thing, so they may have said, okay, I know intuitively that C is, this is the interval of correct numbers, and I'm going to try to generate all of these using this approach. And there's one gaping problem in this approach, which is that you can only generate a countably infinite number of numbers from these sums, right? Oh shoot. Starting to get a little more unstable. Let me fix this. So there's only a countably infinite number of these sums, but you're trying to show that you can attain every C in an interval, which is uncountably infinite in measure. Okay. So I don't know what measure rigorously is, but okay. So that's the problem, right? So that's something that we don't want to pursue. And this is also a common thing. Like when you're, as you get more experience, when you're analyzing your approaches, you can sometimes use like a meta argument to show that one of them is not going to work, right? And that's something you also want to be thinking about. You don't want to be chasing like I don't know what the expression is, but like you don't want to be chasing something that's not going to work. So anyway, that was kind of a tangent, but one thing we do know though is like when we're computing Riemann sums, we know how to compute the Riemann sum of, well, I'll just do it. So like, let's say, you have a Riemann sum with evenly spaced intervals, then you can actually get a closed form for this. So what you can do is, here, wait one sec. Let me close the door. So what you can do is say, so let's say that we have n evenly spaced intervals. Each of the widths is 1 over n, right? And each number is at position I over n. So what you end up getting is the sum from I equal to 0 to n of xi squared times xi minus 1. Now, the width of each of these is actually going to be the same, 1 over n. And you should really like use the picture to understand this better. And so this is equal to, now the width is 1 over n. xi is I over n if we're doing a right-hand Riemann sum. So this is I squared over n squared. Okay. Then we can pull out a 1 over n cubed times the sum from I equal to 0 to n of I squared. Okay. And this sum, you should know the formula for this, n times n plus 1 times 2n plus 1 over 6. So you end up getting that using evenly spaced intervals, Sn equals n times n plus 1 times 2n plus 1 over 6n cubed. Okay. And you can actually see as n goes to infinity, this approaches a third, like it should. So the question is, like, we know that we can attain all of these values. How do we show that we can get everything in between? And when I thought of this, I thought, okay, like when we first did our first approach, when we used 2 jumps, what we did was we said, the function, the cost function looks like this. We know we can attain this value and we can attain this value, so we can get everything in between. That's intermediate value theorem. Okay. And the intermediate value theorem is something that's super important. Okay. And it also, of course, relies on the function being continuous. So I'm thinking here, the question is, I know I can attain these points, right? These values. How do I get everything in between? The answer is intermediate value theorem. But applying it is not completely obvious here, okay? Because with intermediate value theorem, you need to have basically a function of one variable, right? And here I just have like a sequence, basically. So I need to think about how I resolve that. So one thing I realized was, let's say that you have some Riemann sum. So this is 0 to 1, right? So let's say that I have a Riemann sum. And this is going to be kind of badly drawn because I'm doing it on a whiteboard and like doing it quickly. Always draw nice pictures. Okay. So here's my Riemann sum, right? Now, what I realized was I can take, and this is not an evenly, this is just some random one, okay? If I take one of these rectangles, right, what happens if I add another point, right? What happens if I split this? So this is kind of hard to see, but what I've done is I've added this point down here as a new jump. And what that means is that instead my approximation has these two rectangles instead of the bigger one, okay? And again, you have to draw the picture to really see this. What that means is that I've actually removed this little area from the original Riemann sum. And that area, I can quantify its size. Furthermore, okay, getting fancy, I've removed this little area. I can also move this point in between these two, right? And as I move this point, this new point that I'm adding, I'm going to get a continuous set of different values of an area that I'm cutting out, right? And that's going to, then I can apply intermediate value theorem. So basically, so here what I can say is, all right, so let's say that this is epsilon away from this point here, right? So let's say that this is A and this is B, and this is going to be A plus epsilon or something. Okay, it's really small. You can't see that. But basically, this little rectangle up here, its base is of size epsilon. So A is the area that I'm cutting out. Its base is of size epsilon. Its height is B squared. Wait, that seems wrong. Is B squared minus A plus epsilon squared. Again, draw the picture. If you don't get this, completely fine. I'm not explaining. It's a tiny picture. You got to draw the picture to see this. But here, this is going to be B squared minus A plus epsilon squared. So if epsilon is, so when epsilon is 0, right? Then, so the cut area is 0 at the endpoints, right? So if epsilon is 0, if epsilon is B minus A, then it's going to be 0 as well. So anyway, this function here is a function of epsilon, and it tells me how much area I can cut out. This much. It also has a minimum value, so I can compute its minimum value using calculus. One thing that's not nice about this, though, and one big problem, is that it's not going to get me all the way there. So it's not going to get me all the way to a third. The thing is, by cutting out this area, I can only change the total area so much, only by a little amount. And it's not enough to, like, the two endpoints that I'm trying to, so the minimum and the maximum that I'm trying to interpolate between to use intermediate value theorem, it's not, the range isn't wide enough. So another thing I thought about was, well, again, I didn't think about this. My teacher recommended it to me, but basically, so what we want to do is we also want to think about, we know all these values, S, S1, S2. So Sn, I'm defining as basically the Riemann sum with n equal subintervals. right? And this is going to be, so that's Sn. S1 is 1. S2 is, I don't know. But when you go to infinity, that's going to be a third, right? So that covers the range we want. Now the question is, how do we interpolate between those values, right? So if I know Sn and I know Sn plus 1, how can I show that I can get everything in between? Now the problem with trying to interpolate between Sn and Sn plus 1 is that all the endpoints are in different places. So when you look at a Riemann sum that uses n intervals versus n plus 1, you know, like all of the endpoints are going to be completely offset. Like you can't easily interpolate between those two things because you have to shift all of the endpoints. But you can, one thing you do know, so the question is, what two, like Sn and S what, have endpoints in the same locations, right? And the answer is S sub 2n, because S sub 2n, all we're doing is splitting each, like we're taking Sn, we're splitting each of those rectangles in half, right? Or at least the x values in half. So Sn and S2n are very similar in that way. So we want to figure out, so we want to think about how do we interpolate between those. So I can get Sn, I can get S2n. How do I show I can get everything in between? Here, if we look at this, right? One big barrier that I was having, so I'm using S3 and S6, but all right, so just pretend that those are evenly spaced, okay? So S6 would look like S6, all we're doing is splitting each of these in half, right? And again, you got to draw the picture to like really understand what's going on, because otherwise it's really confusing. So S3 is these big rectangles. S6 is when we remove these. Okay, that's S6. One issue that I was running up against was I was trying, so here we really have freedom. So what we can do is think about, you know, when we want to interpolate between Sn and S2n, we can take this point here and this point and this point, and we can move them in any way we want. We actually have n degrees of freedom, right? And I was trying to show that, okay, I have these n variables, and if I you know, vary them in some way, then I can get from Sn to S2n. Now you can't really apply intermediate value theorem on something like that. It's too, I don't even know if intermediate value theorem I don't even think it exists in higher dimensions, for example. And it's way too hard conceptually. And finally, and I'm beating around the bush, but this is how the process goes. Okay. I realized that combine. So first realization, splitting one box is not enough. Okay. Adding only one endpoint and getting rid of this little tiny area, not enough to get me from Sn to S2n. Splitting all n and then interpolating all of them, too complicated. So what if I split all of them, but I still make it a single variable function by letting the distance that I vary away from the left endpoint be epsilon. So what I'm doing here is I'm splitting all of them, right? So here, what I'm going to do, here's epsilon. So this is going to be 1/3 plus epsilon, and this is 2/3 plus epsilon. So I'm splitting all of them. Okay, I'm splitting all n, but it's only a single variable function because there's only one factor that's basically, there's only one number that's determining. Oh, you cannot see that at all. Damn. Okay. There's only one number that you're actually varying. Okay. And I'm so sorry that that's not visible, but there's only one number that's actually varying. And what you can do is define. So you define Fn of epsilon as basically the Riemann sum that you get you get, when you split each rectangle in Sn by adding endpoints at epsilon, 1 over n plus epsilon, 2 over n plus epsilon, all the way to n minus 1 over n plus epsilon. Okay. So that is the function I've defined. And fn of 0 is Sn. Fn of 1 over 2n. So when I split each of the intervals exactly in half, I get S2n. And so here I have a single variable function, a function of epsilon, which varies between Sn and S2n. I can get everything in between. So therefore, by intermediate value theorem, I can get everything in between. And that's the big idea. I basically proved the problem. Okay, now I need to write the proof. But that's the big idea. Okay. So yeah, I mean, it's a B2 for a reason. Okay, I know that one's a doozy. So you basically say, okay, Fn of 0 is Sn. Fn of 1 over 2n is S2n. Okay, if you split it in that way. Fn is continuous. Therefore, you can get everything in the interval S2n to Sn. And then you can show that you can get everything between 1/3 and 1. Because you can get each of these partial sums and you get everything in between. Okay, no viewers. I don't blame you. All right, so no viewers. I'm going to take a quick break after that one. I'm not going to write the proof because it's very long. But yeah, I'm going to take a quick break. I know I lost a lot of people. I don't blame them. My pictures were small. But yeah, and then we will get into 2015 A3 soon. I probably should have saved B2 as the hardest one. No, A3 is hard too. Oh, okay. Your dad is watching? Okay. Hi, Mr. Derubis. I also need extra seat belts when Bella drives me. So I wish I had that too. Anyone else watching? Like I said, no hard feelings if not. I know this is like not what everyone wants to be doing on their break. Okay. Oh. This is a doozy, okay? It is a marathon after all. I mean, I know I got tap water. I know. I got the sink water. Got my bathroom sink water. Dang, I definitely lost a lot of people with the last one, but all right, we'll start at 5:05. I don't think anyone else is coming, but that's okay because I need this for my own practice. This is a hard problem. I'm quite. Don't worry. Don't worry. Honestly, I was kind of confusing myself a little bit. Actually, no. Well, I understand what I'm saying, but I've also been working on the problem for a long time. Okay, I just saw the number go up. Did someone else just join other than Bella? Do we have another viewer? Please say something in the chat. I guess not. That's okay. All right, let's go ahead and do our final problem in this marathon. Okay, we're in the home stretch. 2015, A3. Now this problem is a hard problem. Okay, it's kind of hard. Okay, but I like it, so we're doing it. So let me just write what the problem is, because it's it's not too hard to write, but like I think that when you first look at it, you kind of want to throw up a little bit. So that you have to figure out what this quantity is. Okay, I'm writing it too big. The whole board isn't enough to contain it. Okay, you have to compute this. Oh, it's probably not even visible. But, I mean, you can see it online. Now, let me explain what's going on with this. So here, now you got a lot going on. So these mean product. Okay, so what I'm doing is, so here I have this expression. It's a function of A and B. I need to write that bigger, but basically it's a function of A and B. You can see this online. And basically I'm saying A can be anything from 1 to 2015, B can be anything from 1 to 2015. That's going to give you a lot of terms. Yeah, okay, thank you. It is kind of hard to see. So I would, okay, if you go to the description, 2015 A3, you can find this online. And then this term here, you got an E going on, you have a pi, and you got an imaginary number going on. Okay, there's a lot going on in this. So let me just explain how I went through this. And you know what? I think I'm kind of, yeah, I should just accept this is gonna be hard. So you have to have a lot of background knowledge for this problem, admittedly. So let's use that. So here, right? First, let's just now with this problem, there were 3 2015s in the problem. That's just the year number. So, like, whenever you have a problem like where you have a year number, that's usually arbitrary, at least somewhat arbitrary. So we're going to test small cases and we're going to vary that number. So let's define A sub n equal to, so an equals, I don't have a big enough board and enough pixels to actually. So the product from A equal to 1 to n, product from B equal to 1 to n of e to the 2 pi I a b over n. Okay. So this is basically the same thing that we're trying to compute, except the log is gone. The log base 2 is gone. So now let's look at this. And so I replaced all the 2015s with n's. Then I'm going to compute, okay, what is A1? What is A2, etc. So A1 is equal to 1 plus, so there's only one, oh, I wrote it wrong. It should be 1 plus. It should be, if you go onto the website and look at the problem there. It should be 1 plus. Now, A1, if you compute it, is just this. 1 plus e to the 2 pi I. And that's just equal to 2, okay, because e to the 2 pi I is 1. So A1 is 2, okay. A2, now that's going to be 1 plus e to the 2 pi I over 2 plus, or times, so there's going to be 4 terms here, okay. And, I would recommend, follow along, write it out yourself, if you are so inclined. So here I'm writing it out. Okay, so we have this 4 terms. Now, really, there's only one term that matters here, and it's this one, the first one. Because what you should notice is that this here is an e to the pi I, and that's -1. Again, you have to, this is background knowledge, right? So complex numbers. So e to the pi I is -1. This is 1 plus that, so this is a 0. So this term here is 0. I just dropped the cap to my marker. All right, this term is 0 in this product, and so this whole thing is just 0. Okay, and in fact, what you should realize at this point is that if this number is even, so we just computed A1, this is A2. If you compute A4, A6, A8, you're always going to get one term which has an e to the pi I, right? You can show this. And so, in fact, if this number is even, then the product is 0. So what that means is, so that's something that we just discovered, okay? Unfortunately, 2015 is an odd number. If it was even, this would be really easy. But basically, you know that A2, A4, A6, they're all equal to 0, okay? So we only care about the odd ones. So now let's look at A3. Now this is going to be, oh my God, this is a lot. Okay. Do I want to write this out? Now you should, if you're doing this, you should write out, and you really want to figure out how to do this problem, you should write out A3. Okay. There's 9 terms. Write out all 9 terms of A3. Okay. But I'm going to skip to A5 and talk about something that's really important. So A5 has 25 terms. And when I was taking the test, I was thinking, I don't want to write all this out. It's not worth my time. But it was, okay? And a lot of times when you're testing cases, you will think like, oh, this is stupid for me to just write everything out. But it's actually going to help you a lot. So there's 25 terms with A5. I wrote all 25 out, and I noticed something very important, which is, first off, the first term for A equal to 1, like small a equal to 1, okay? The first term is 1 plus e. So not visible. Okay. 1 plus e to the 2 pi I over 5. 1 plus e to the 4 pi I over 5. 1 plus e to the 6 pi I over 5. Okay. 1 plus e to the 8 pi I over 5. 1 plus e to the 10 pi I over 5. So this is when small a equals 1 in that product. This is the first sort of mini product. Couple notes. So this here, e to the 10 pi over 5, that's just going to be just 1 because 10 pi over 5 is just 2 pi. So that's the product for a equal to 1. Now the product for a equal to 2 is going to be, all of these will be double. Okay. So this is going to be 4, this will be 8, this will be 12, 16, and 20. But what's really important to realize, and yeah, it's, the blur is kind of bad. So it's 4, 8. So these numbers are 4, 8, 12, 16, and 20. Okay. Is that these numbers, so like, you only care about like what okay, e to the 12 pi I over 5 is just e to the 2 pi I over 5 because e to the 12 pi I over 5 is equal to e to the 2 pi times e to the 2 pi I over 5. Like if this angle in the exponent is greater than 2 pi, then you can take 2 pi's out of it, right? This here, 16 pi over 5, that's just 6 pi over 5. 20 pi over 5, I'm going to write as 10 pi I over 5. And what that means, if you actually look at this, this is the same as the first product. So here's the e to the 2 pi I over 5. Here's the 4, here's the 6, here's the 8, and here's the 10. And this is because what we really only care about is the numbers mod 5. So here, for a equal to 1, we have the numbers 2, 4, or we have basically so we have 2, 4, 6, 8, and 10. For a equal to 2, we get 4, 8, 12, 16, and 20 in the exponents. But we only care about these numbers mod 5 or mod 10. So here, this is 2, this is 6, okay? And this you can write as 10. And it's actually the same set of numbers, okay? You need a black marker. Yes. Well, yeah, my black markers are kind of out. That's it. Okay, that works okay. All right. So, yeah, I do. Okay. All right. So here, if we look at this, right? The idea is if you look at 1, 2, 3, that's better. Yeah. Okay. 4 and 5, right? Then we look at the numbers 2, 4, 6, 8, and 10 mod 5. These are going to, oh, wait. I meant, yes, mod 5. These are going to be equivalent. So this is going to be 1. This is going to be 3, and this is going to be 5. It's the same set of numbers. And I don't know what the formal, thing you say is for this. Like, basically, if you look at the numbers, like, in general, if you look at the numbers A, 2A, 3A, 4A, and 5A, mod 5, where A is 1, 2, 3, 4, or 5, it's going to give you the same set of quadratic, or not quadratic, same set of modular residues. Now, this is a result that I learned from like number theory in high school, but this is something you also, I think, learn in abstract algebra if you've ever taken abstract algebra. So this is going to be really important because what it basically means is that, so for computing like the product for n equal to 5, you get 5 products of 5 terms. But each of these 5-term products is actually going to be the same, except for the last one. The last one is going to be 1 plus e to the 10 pi I over 5. Okay. Oh my God, it's glare. 1 plus e to the 20 pi I over 5. Okay, dot, dot, dot. 1 plus e to the 50 pi I over 5. Okay. And all of these are going to be, this is going to be e to the 2 pi, e to the 4 pi, e to the 6 pi. They're all going to be 1. So the last term is just going to be 2 times 2 times 2 times 2 times 2. You're going to get 5, 2, so 2 to the 5th. Okay. But all the other terms, all the mini products are the same. Okay. So what we want to do is figure out what is that product. So what is 1? So what is 1 plus e to the 2 pi I over 5 times 1 plus e to the 4 pi I over 5 times 1 plus e to the 6 pi I over 5 times 1 plus e to the 8 pi I over 5 times 1 plus e to the 10 pi I over 5. What is this? Okay, what is this? Now, the first thing to recognize is that these, okay, and you have to have some experience with complex numbers. These are solutions to the polynomial z to the 5th equals 1. Okay, so these are all the 5th roots of unity, if you know what that is. Basically, z to the 5th equals 1 has 5 solutions. Okay, in the complex plane. All of them are evenly, so you have one is obviously a solution, and then you have evenly spaced angles around the unit circle in the complex plane. Okay, so these are all the fifth roots of unity. Okay, but the thing is, we have these ones attached, right? So that's annoying. So what we think of is what happens when we take basically what this means is that, now I was thinking geometrically about this, but I don't want to draw the picture. But here, these are all roots to the polynomial z minus 1 to the fifth equals 1. Okay? So if we do z minus 1, we get just the bare e terms, the roots of unity, and then to the fifth equals 1. So all of these are roots to this polynomial, and we want to compute the product of the roots of a polynomial. We can get that through the constant term of that polynomial using Vieta's formulas. So here, let's look at this here, right? Now z minus 1 to the fifth equals 1, right? So let's compute this polynomial. Now, in fact, it actually doesn't matter. All we care about is the constant term. The constant term is going to have a minus 1 to the fifth, and then we're going to subtract another 1, right? This here, this constant term is going to be minus 2. And using Vieta's formulas and the fact that 5 is odd, the product of those terms is going to be positive 2. Okay, so Vieta's formulas, you need to look at the degree of the polynomial to determine whether you flip the sign on the last one. So we know that mini product is just 2. Okay, all of those 5 terms. And so we have 4 copies of that. So what we have is, for a equal to 1, we just get 2. For a equal to 2, that product is also 2. It's the same thing. It's the same thing. And the last one is 2 to the fifth. Okay, because we get 5 copies of 2. Then we multiply that together, that's 2 to the 9th. Okay? 2 to the 9th. So that's A5 is 2 to the 9th. And now we see where the log base 2 is coming into play, right? Because log base 2 of that is just 9. We only really care about the exponents. So now let's think in general. Okay, well, no, not yet. So one problem with this is, so 5 is prime. What that means is that everything, so 5, if you look at a prime p, everything from 1 to p minus 1, when you do this process, is going to be, these are all going to be the same. Okay, and this is like a result from number theory, right? So, right, okay. So the question is, what if this is composite, right? What if we look at 15, n equal to 15, for example? So for n equal to 15, so when we look at these products, okay, now if the GCD of A and 15 is 1, okay, so if, and also what I'm going to do here is define Bn as log base 2 of An. So this is just saying, okay, now I'm only going to focus on the exponent. So if I look at, so I could have A equal to 1, 2, 3, 4. A could be anything from 1 to 15. And I'm going to get, products of 15 terms. So I'm evaluating this big product. If the GCD of A and 15 is 1, okay, then I'm going to get the same product repeatedly. And it's actually going to be equivalent to when A was equal to 1, which is going to be all of the 15th roots of unity. Okay, so that was a lot in one sentence. Basically, when GCD of A15 is 1, then when you compute, when you actually get those products of 15 terms, they're all going to actually be the same. Okay, because you can take out powers of, you can take out 2 pi's out of the exponent. You only care about what they are, mod 2 pi. And so when you have this true, they're all going to be the same product. They're all going to be equivalent to when A was equal to 1, which is going to just be 2. The total product of 15 terms will just be 2, because they're all solutions. Oh yeah, and I should have said this. Those will all be solutions to the polynomial z minus 1 to the 15th equals 1. Okay? And this here is still going to have a constant term of -2 because this power is odd, right? And because this power is odd, also, we're going to take the negative of the constant term. So it'll just be +2. This also applies in general. So we really only care about computing this whole thing for n that's odd, because n even gives you a sub n for n even is 0. So we know that we can make this argument in general, is that this is going to be just be 2. So if GCD of a and 15 is 1, we only get a single power of 2 out of all of those. So that means that there are totient of 15 powers of 2 we get in total from that. Now, if you haven't seen this, again, no worries. This is the Euler totient function. So it basically tells you the number of numbers that are less than 15 that are relatively prime to it that satisfy this equation. So this is actually like a definition, basically. Okay, anyway, I told you this problem is going to be like really freaking hard. Okay, so a lot of background knowledge. Okay, so but what if a is like 3? What happens there? Okay, so if a is 3, okay, what we actually end up getting, so a is little a is 3, okay, and n is 15, okay, then what ends up happening is, so now again, I'm kind of rushing this, but you would write out all of the terms, all 15 terms, you write them all out, and then you simplify them. And what you realize is that if you look at the first 5 terms, right? So you get 1 plus e to the 3 pi I over 15, 1 plus e to the 6 pi I over 15, 1 plus e to the 9 pi I over 15, 1 plus e to the 12 pi I over 15, and then 1 plus e to the 15 pi I over 15. Wait, sorry. These are all times 2. 6, 12. I need new markers. Okay. This here is 18. And I know this isn't visible. Okay. Like I said, I'm explaining how you do this. So you should plug this in and write it out for yourself if you want to see all the details. Big idea with this is that all of these fractions simplify. So 6 pi I over 15 is the same as 2 pi I over 5. Right? 12 pi I over 15 is divided by 3, 4 pi I over 5. This is going to be 6 pi I over 5. This is going to be 8 pi I over 5, and this is finally going to be 10 pi I over 5. So in fact, when a is 3, the first 5 terms are going to be the exact. So when a is 3 and n is 15, the first 5 terms are the exact same as if a was 1 and n was 5, which makes sense because all of the fractions will simplify. And we know that this product is 2, as this product is 2. More generally, I'm thinking recursively, this product is, well, actually, no, I will get to that later. So we know that this is 2. And then we also have, now again, we have 15 total terms. I've only counted for 5 here. But in fact, there's the next 2 sets of terms. So there's 3 groups of 5. Each group is going to be equivalent because the next term is going to be 1 plus e to the 36 pi I over 15, which is the same as 1 plus e to the 6 pi over 15, okay, because we just take out a 2 pi. So you actually get 3 copies of the same exact term. So you end up getting a 2 cubed, okay, because each of these 5 makes 2, and then you end up getting 2 cubed because you get 3 copies of the same term. So, all right, I know I'm blasting through this one, but all right. So this is big news. Okay, well, actually, there's a couple other things. So we know that now when we generalize this idea, when we look at So a equal to 3, n equal to 15. So when we look at a being 3, 6, 9, 12, or 15, right? A could be any of these, multiples of 3. This is actually going to be the same as a being 1, 2, 3, 4, or 5 for when we were computing, b sub 5. Okay? So basically, these 5 cases, what that means is that these terms, when a is 3, 6, 9, 12, and 15, they're all going to contribute b5 powers of 2. But actually, they're going to contribute b5 cubed powers of 2 because we always have 3 copies of the same 5 terms for each of these products. So, in fact, no, wait. Not b5 cubed, 3b5, because b5 is the log base 2. So we're only counting the exponents. So here, these terms contribute a 3b5. Okay. So let me, I'm working towards getting that formula. So, all right. So a could be anything from 1 to 15. So if GCD, I just need to get new markers. That's what it is. GCD of a and 15 is 1. That's going to give us totient of 15 powers of 5. Okay, because there's powers of 2 because there's totient of 15 numbers. Each of them only gives us 1 power of 2. When a is 3, 6, 9, 12, or 15, okay, that's going to give us 3b5 powers of 2. 3b5. When a is 5, 10, or 15, same logic as before. You want to run through it. It's going to be 5b3. Same logic that I said before. And then we've overcounted. So we've counted the a equal to 15 case twice. So then we need to subtract. So the a equal to 15 case is going to just be 15 powers of 2. If you plug it in, you can see that. So that's just going to be this is going to be minus 15, or this is going to be 15 powers of 2 for the a equal to 15 case. So what we want to do, so we say is b15 equals the totient of 15. God, these markers suck. Okay. So b15 is going to equal totient of 15 plus (3b5) plus 5b3 minus 15. And I'm going to say b1. Okay, 15b1. Now b1 is just 1. The reason I'm doing this is because of this structure. So 3b5, 3 times 5 is 15, 5 times 3 is 15, 15 times 1 is 15. Okay, just because I'm trying to see if there's a pattern. So what we can see here is that in general, if this number here is a product of 2 primes, PQ, then B sub PQ is totient of PQ plus P B sub Q plus Q B sub P minus PQ B sub 1. And then we can use recursion. So B sub 5, now if you're computing B5, basically when this is prime, it becomes easy because let me leave this formula up. When you're computing this for a prime number, okay, B5, for example, we know that A equal to, so we know that we end up getting, so for GCD of A and 5 equal to 1, we end up getting totient of 5, right, which is just 4. Okay, so you end up getting just 4 powers of 2 from each of those because, if if n is a prime number, then everything less than it is relatively prime to it. So, and then for the A equal to 5 case, we get 5 powers of 2. So we end up getting basically, B sub P is equal to P plus totient of P. And totient of P is just P minus 1. So B sub P is 2P minus 1. Okay, so this is like our base case. And again, if you really want to understand this problem, I would verify this on your own. BP equals 2p minus 1. So here we can evaluate this this thing. We can evaluate this sum by using this formula. Okay. Now finally, let's get to B sub 2015. So B 2015. Now what I'm going to do here is actually look at. No, I'll look at B 2015. So 2015. Oh my God. B 2015 is 5 times 13 times 31. So this is 3 primes. This isn't something that we've looked at yet. And actually, for the sake of time, I'm not doing this, but what you should do is look at B sub 105. Because that's 3 times 5 times 7. You want to look at what happens in that case when you have a lot more moving parts, okay? Because you have 3 primes. And you have to use the principle of inclusion exclusion, okay, PIE, to evaluate this. But what you end up getting is B 2015 equals totient of 2015 plus, okay, 5B, so 5B 403, which is this product, okay, plus 13B 155 plus 31B 65. Okay, so that's the first sort of group of terms. And again, you have to use an example case to get this, okay, to really understand this. Now what we need to do is use principle of inclusion and exclusion. So let's say that, what if A was a multiple of both 5 and 13, then we've double counted, right? So if A is a multiple of both 5 and 13, it's a multiple of 65. So we end up getting, for these terms, we end up getting like 65B31 plus 155B13 plus 403B5. And then finally, if you think about, okay, the A equal to 2015 case, we've counted it 1, 2, 3 times, subtracted it 1, 2, 3 times, so we need to add it back in. Okay, this is the principle of inclusion exclusion. Okay, PIE. It's I don't know where you'd learn this. Some kind of combinatorics class or something. Okay. Again, this requires a lot of background knowledge. Like if you don't, it's fine if you're completely lost. So that's what you end up getting. And from this point, you have 2 options. Your first option is compute this, because you can actually, it's a lot of computation, but you can actually get the answer from this. I would not advise this, even though you may be tempted to just do it. I would say that, like what I did was I tried to think about how I could simplify this even further. So what I realized was that, basically, like if you expand these terms, so these terms here, the B403, B155, and B65. Oh my god, my Mac is on 5%. Okay, I'll wrap up. So here, if you expand these terms, right, then you can simplify this down. Okay, and I'm at 5%. Basically, if you replace this with B sub PQR, so replace it with B sub PQR, you use variables. This is a case where variables are going to help you. And you simplify this all the way down. You actually end up finding out that B sub PQR equals 2P minus 1 times 2Q minus 1 times 2R minus 1. Okay. Right. That's what it ends up equaling. Because this is, well, basically, and this is a really bad explanation because I haven't shown you, but essentially what you get is you get every term. If you were to FOIL this out, you get every term in that product. So you can factor it like this. And so what that means is if you plug in P equal to 5, Q equal to 13, and R equal to 31, you end up getting the answer, which is, so plugging in, so that's 9 times 25 times 61, which I believe is 13,725. And that's the answer to the problem. Okay. Okay. I really saved the least amount of time for the last one, didn't I? So that's how that's kind of that's how you do it. Okay. That's how I did it. There's a solution on the website, which you may think is better. I think it's better in some ways. But yeah, so thank you. All right, let me plug in my laptop and sit down. Okay. Before it dies on me. Okay. So thank you everybody for coming, especially if you stayed the whole time. You know who you are. Thank you. Wow, that was a lot. That's the longest I've ever done. So yeah, like the later problems, normally for that last problem, I would dedicate a whole stream to that. Normally I'd spend a whole hour and a half to 2 hours talking about that one problem specifically, which is why I was going so quickly through it and didn't really dig into it much. But especially, for most people preparing for the exam, you should really focus on the earlier problems like A1, A2, and B1. Now, in general, sometimes there are later problems which are doable, but don't be pushing too high. Don't be pushing into too high territory in general, is my advice. Although, you also want to make sure that you consider every problem and that you don't overestimate the difficulty of a problem. Let me turn on the light. I'm much more my brain is much more kind of, normally at the end of streams I'm kind of brain dead and but I'm still there. I'm kind of I'm holding on right now. So yeah, so the Putnam exam is next Saturday. I hope everyone at Pitt that has signed up is practicing. Okay. And yeah, and I will do another stream next week. Next Wednesday, a week from today, probably. And I will see you then. Make sure to smash like and subscribe as always, and have a good day. Thank you for staying the whole time. Amazing.